Hello and welcome to Stats of Chaz. I'm Dr. Charlie Collins. You might hear a little fan in the background. That's because it's very hot. It's the middle of summer, and so that's what we got. So today I'm going to discuss regression and correlation. I'm going to cover the conceptual issues or conceptual uses rather of regression and correlation, and under what conditions to use them. So what is regression and correlation? These are statistical methods used to examine a relationship between two variables, each of which is measured at the interval ratio level. These two methods set out to first identify if there is a relationship between two variables, examine the strength of the relationship, and look to see in which direction the relationship exists, meaning as one goes up, which way does the other one go. There are a couple main differences between regression and correlation. For one, correlation can only handle two variables. Let's call them variable x and variable y. This is typical notation for regression and correlation. While correlation can handle x and y, regression can handle x, y, z, and even w. In fact, in a regression model, a researcher can include a theoretically infinite number of independent variables in relationship to one dependent variable. This is what we call multiple regression. This is beyond this talk, but it's an extension of the current bivariate regression that we'll be talking about today. The second main difference is that regression is a predictive statistic, and correlation is not. What I mean by that is that by using the regression equation, I can predict a score of a variable y based on the observed score of variable x. In other words, I can predict what should be a score on the dependent variable based on the score of the independent variable given our slope and intercept. So let me give an example of policing and crime within cities. Suppose I have a hypothesis that as the number of police officers in a city increases, the number of crimes also goes up. This may be counterintuitive, which is totally fair and against your hypothesis. Let's just say this is my hypothesis, right? So in this scenario, police officers are represented by the notation x, so also known as the independent variable, and crimes are represented by the notation y, aka the dependent variable. In this scenario, regression and correlation help me identify whether there's a relationship between these variables, the strength of the relationship, and the direction of the relationship. In other words, is there a relationship between the number of police and the number of crimes? To what extent do police perhaps influence crime? And in what direction? The first two questions here may be fairly clear, but what does direction mean? The direction refers to the slope of the relationship. A positive relationship means that the more cops a city has, the more crimes they see. A negative relationship means that the fewer officers a city has, the more crimes they will see. You can see this relationship here, hopefully, without my light glaring. So in this case, we have a positive relationship, right? So as crime increases, as officers increase, so does crime. Here, you can see a negative relationship, whereas the more officers you see, the less crime. So there's a reduction in crime. Both regression and correlation can do these things for us. But this is where they diverge. When trying to predict observed scores of x based on observed scores of y. That is, regression can predict a city's level of crime based on the number of police officers. To do this, we can use this equation here. Now, I've skipped a couple of hand calculations, but what we can do is we can use things like SPSS or Excel to calculate this stuff for us. So here what we have is y equals a plus b times x, where y is the score on a dependent variable, A is the intercept, or the place where the regression line crosses the y-axis. B is the slope of the regression line, and we can think of this as the strength of the relationship between x and y. And then x is the score on the independent variable. So suppose we're trying to predict the level of crime in a city with 200 police officers. So that would be our x variable. We take our regression output from our observed data to get our intercept, which, let's say in our case, is 70. This means that in a city with 0 police officers, there would be 70 crimes on average. And we get our slope, which happens to be negative 0.25, which means that for every officer in a city, the number of crimes are reduced by 0.25. Or, to put it another way, every 4 officers in a city contributes to a reduction of 1 crime. Now, what we can do with regression is predict the number of crimes that should occur in a city with a given number of officers. Let's say 200, we're just interested in 200, maybe our city has 200. And so we're going to use the data to predict this. So what we can do is we can plug in those numbers. So we leave our y blank, right? And then for A, we can plug in our intercept, which in our case is 70. And then for B, we can plug in our slope, which is negative 0.25. And then for X, we can plug in 200, because we're interested to know how many officers for our particular case. So once we plug in the numbers, we can get an outcome of 20, right? Or not we can, but we do get an outcome of 20. And you can write this out on your own. What this means is that in a city of 200 officers, we should expect to see about 20 crimes in that city. You may be thinking to yourself, this seems a little inaccurate. Seems like a lot of officers and a very small number of crimes. And you're right, the accuracy of these predicted values depends on the strength of the relationship between x and y, which is where the correlation comes in. Also, side note, I made up the numbers, so these were used just as an example. Using the correlation coefficient, we can find the strength of the relationship between x and y, which is something your stats package can calculate for you. So when you run your SPSS or your Excel or your R, whatever stats package you use, look for a value called R squared. In my simulated data, my R squared was very small, telling me that the number of police in a city is not strongly predictive of the number of crimes. So, although regression can tell me the predictive value of y given an x value, the relatively small correlation between the two means that there may be a lot of error in my prediction. Or, what is more likely the case, there are a lot of other factors in a city that contributes to crime, not necessarily the number of police in a city. So that's all I have for today. By now you should know what correlation and regression do, and under what conditions to use correlation and regression. Thanks for watching Stats with Chaz, and I will see you next time.